Swayam Prabha. Digital India. Educated India.
So this is a case where all shortest paths from V1 to Vj, Vi to Vj, using only vertices in V1 up to Vk as intermediate vertices do use Vk. So while in the previous case it does not use Vk, in this case it does use Vk. Okay, all the shortest path use Vk. Okay, in this case the shortest path construction would look as the following: Vi Now you see this has to happen. Let's see why. Now as Vk cannot be an intermediate vertex on the subpath from Vi to Vk, okay, it cannot include Vk, right? So Vk cannot be an intermediate vertex on the subpath Vi to Vk. So this means that the subpath's length, this indicates that the length of the subpath should be Ik. Why? See, from Vi to Vk, so we are actually computing the shortest path from Vi to Vj, and this shortest path has Vk as an intermediate vertex for all such shortest path constructions from Vi to Vj. Okay, this is our case 2. Now we break this case into two parts. Okay, one is we try to reach from Vi to Vk and then from Vk to Vj. Now when we try to reach from Vi to Vk, you can immediately imagine that Vk cannot be part of this subpath because it cannot be part of this of the intermediate vertices in this subpath because it is the endpoint. Okay, so therefore the length of the subpath here should be dk minus 1 Ik. Okay, now this length cannot be or let us say this length is the shortest path from Vi to Vk. Now question is why? Okay, now Now there cannot be any subpath shorter than dk minus 1 ik, because by the basic assumption this is the length, because dk minus 1 ik is the length of the shortest path from vi to vk, considering only v1 to vk as intermediate nodes. On the other hand, dk minus 1 ij cannot be longer. Why? If it was so, then we could have replaced it by the shortest path. Okay, as apparent from the figure that we have just now seen. Okay. So if this was longer, dk minus 1 ij was longer, then you could have always replaced it by the shortest path. So this is by our underlying assumption. So the same thing holds for the other side. So we have shown it from for vi to vk. The same set of arguments holds for vk to vj. So this is basically the length here basically is dk minus 1 kj. Okay. So therefore, in case 2, the length, the shortest path length is dk ij is equal to dk minus 1 ik plus dk minus 1 kj. So you see, this is the crux of the whole problem. We have now been able to get the optimal substructure. So dk for any value of k from 0 to n, dkij is equal to dk minus 1 ik plus dk minus 1 kj. So this is the optimal substructure. So the larger shortest path includes in it subpaths which themselves are also shortest paths. Okay, this is what is being reflected by the equation that we have written out here. So an example for our particular use case graph is CD253, if you see, is equal to 7 is equal to 4 plus 3. This is D152 plus D123. Okay. So this is how you solve the problem using the optimal substructure idea. So combining case 1 and case 2, we now have dk ij is minimum of dk minus 1 ij and dk minus 1 ik plus dk minus 1 kj, where the first term is a contribution of case 1 and the second term is a contribution of case 2. So now using this recursive formula, we can build the recursive or iterative, whatever way you think of it, we can build the D matrices, and finally from there we can actually get the shortest distance matrix, the lengths. Okay. So some examples we can try to compute from for our running use case. Say if we want to compute D1 to 4, this is minimum of D0 to 4 comma D0 to 1 plus D0 1 4. This is minimum of 2 comma 9 plus 1, which is 2. In this way you can keep computing for every individual cell of the D matrix. Okay. Now once you have this D matrix, it's kind of child's play to obtain the shortest distance, length of the shortest distance between any pair of vertices. This algorithm is known as the Floyd's algorithm for shortest paths. Okay, so here the input is the matrix W and N. Output is D. Okay. So how do you compute this? Very simple. You initialize D to W, then you just have 3 for loops. Just simply writing down the iterative formula that you have obtained. Okay, so Dij is the minimum of previous Dij and the current Dik plus Dkj. Okay, and this gives you the distance matrix immediately. And as you can understand, it's very easy to compute the every case time complexity, which here is order of n cube. So our Tn is O of. Okay, so far we have only seen how to construct the distance matrix. So we have been able to start with W, and through an iterative process we have been able to construct D. However, what is left is now to construct the actual shortest path and print it. So we have to now construct the shortest path and print it. We have only got the distance matrix representing the shortest path distances between every pair of vertices. Now we have to modify the Floyd's algorithm to also be able to print the path. So we will have the same setting. So the problem now is again the same. We have to now, not only construct D from W, but also create the shortest paths. Shortest paths. For this, in addition to whatever we have uh, uh, produced as outputs in the previous algorithm, we will produce another output. This is an additional output, which is a 2D array P, okay, with both rows and columns running from 1 to n and is defined as follows. So Pij is the highest index of an intermediate vertex on the shortest path from Vi to Vj if at least one intermediate vertex exists, is zero if no intermediate vertex exists. So basically what you do is you construct another 2D matrix P. You can imagine it to be kind of a path matrix where you store in every cell the highest index of an intermediate vertex, okay, in the shortest path from Vi to Vj that you have explored, uh, in case there is at least one such intermediate vertex. If there is no such intermediate vertex between a pair of vertices, then you put this as zero. Otherwise, among all the intermediate vertices that appear on the shortest path between Vi to Vj, you put the one that has the highest index. So how do we achieve this? Again, we just simply modify the previous code that we had to include the construction of P. So as simple as that. So you just see that the minimality condition that we had checked earlier, that we have broken here, okay? And why we have broken? So that we could actually also record the highest index on that path, okay, in Pij. So the K are the intermediate vertices, if you remember, and as many times this condition is satisfied, the optimality condition that Dik plus Dkj is less than Dij is satisfied, we keep on updating Pij, and this is how the Pij gets the largest index or the highest index between V1 and Vk, okay, in the shortest path from I to j. Now, if we consider our running example, the path matrix that we will land up into is as follows. So if you recall, there were 5 vertices. So this is our P matrix. Now, once we have constructed this P matrix, we can easily use this P matrix to compute the shortest path, okay, to print the shortest path. That is very easy. So the problem here is print shortest path. So in more specific, problem is print the intermediate vertices on a shortest path from one vertex to another. This is your problem. The input in this case is the 2D array P. Okay, output is the intermediate, of course. So along with the 2D array P, the source and target vertices. Let's call them VQ and VR. Output, the intermediate vertices on a shortest path from VQ to VR. Okay. So how do we write the code for this? Very simple. It's kind of a traversal on this matrix. Index Q and index R. So these are the indices corresponding to the two nodes. If P of QR is not 0, then you recursively call path Q and whatever is there on PQR. You again call the path function with PQR and R as the arguments. So you see what is happening. This is very similar to the traversal algorithms that you have already learned in your binary search traversal techniques. Okay, so let's say if I call the function path and my arguments for Q and R are 5 and 3. That is, I want to print the vertices that are on the path or on the shortest path connecting 5 and 3. So I would find out, first of all, P 5 3. Okay, so this, according to my P matrix, if you see, P53 is 4. Okay, so this is equal to 4. So now, therefore, I will call the function path 5 4. Okay, now this will again bring me to a new call where I will check P 5 4. Now I will see what is P54. P54 is 1. So this is 1. This is still not 0. Okay. Then I'll again call P or path 5 1. Now path 5 1 is P 5 1 and P51, as you see, is 0. So this is 0. Now we have to stop here and keep on popping up the recursion stack. Okay, and therefore we get to print V1 and V4 consecutively. Okay, and then you will go to the other side of the path call and you will see that all of them are yielding zeros, and therefore you do not need to print anything else. So then this amounts to telling that the path connecting from V5 to V3 goes via V1 and V4. Okay, so this is the shortest path from V5 to V3, and you, from the distance matrix D, you already know what is the cost or the length of this path. So in this way you accomplish the task of not only finding the length of the shortest path but also the exact path. So we will stop here. In the next lecture we will take up another interesting problem which also comes very often in in various computer science applications, and that is sequence alignment. So we'll specifically look into one such sequence alignment problem, um, like which is quite popular in the computational biology literature. There are many sequence alignment problems, but we will take this up because this has a real world application hidden in it.